There is a moon orbiting Jupiter right now that should not be as interesting as it is. By every surface measurement, by every visual impression you get from a photograph, Europa looks like a mistake. It looks like someone took a billiard ball, wrapped it in cracked white plastic, and hung it in the dark about 780 million kilometers from the sun. It has no atmosphere worth mentioning. Its surface temperature averages around minus 160 degrees Celsius. It has no mountains, no volcanoes visible from space, no dramatic weather systems, no rings, no moons of its own. It is, from the outside, one of the most featureless objects in the entire solar system. And for decades, that's roughly how scientists treated it. Europa showed up in textbooks the way a minor character shows up in a novel. Present, acknowledged, briefly described, and then shuffled off stage while the more dramatic players took over. Mars got the rovers, Venus got the radar mappers, Titan got the haze, and the hydrocarbon lakes and the excited press releases. Europa sat quietly at the edge of the conversation, neither demanding nor receiving much attention. But here's the thing about quiet objects. Sometimes they're quiet because there's nothing happening. And sometimes they're quiet because everything is happening somewhere you can't see it. Europa belongs to the second category. Beneath that smooth, cracked, boring-looking surface, something has been going on for a very long time. Something warm, something wet, something that, by every right, should not exist on a moon this small, this cold, this distant from any meaningful source of heat. And in the last 2 years, the James Webb Space Telescope has done something no instrument in human history has been able to do. It looked at Europa carefully enough, precisely enough, with sensitive enough instruments, that Europa couldn't stay quiet anymore. What Webb found is not terrifying in the way a disaster is terrifying. It's not an imminent threat, it's not a warning sign. It's terrifying in a different and more profound way. The way that standing at the edge of a canyon is terrifying. Not because it's going to hurt you, but because you suddenly understand in your bones the true scale of what you're looking at, and you realize you've been thinking too small. Let's go back to the beginning, because the backstory matters, and it's stranger than most people realize. Galileo Galilei discovered Europa in January of 1610, along with 3 of Jupiter's other large moons, using a telescope he had built himself. He was looking at Jupiter almost every night, trying to figure out whether these tiny points of light near the planet were stars or something else. They moved. Stars don't move like that. What he had found were 4 worlds orbiting Jupiter: Io, Europa, Ganymede, and Callisto. The first direct observational evidence that not everything in the solar system orbited Earth. This was, in the context of 1610, a politically explosive discovery. The Catholic Church had opinions about that kind of thing. Galileo had a difficult few decades ahead of him as a direct result. But that's a different story. The point is that Europa has been known to humanity for more than 400 years. And for most of those 400 years, it was just a dot. A small bright dot near a large bright dot, visible through backyard telescopes on a clear night, noted and cataloged and otherwise left alone. Then came the Voyager missions. In 1979, Voyager 1 and Voyager 2 flew through the Jupiter system in quick succession, snapping photographs as they went. When scientists got their first close-up look at Europa's surface, they expected to see what you see on most moons in the outer solar system: craters. Lots and lots of craters. The moon's surface should have been pockmarked from billions of years of meteorite bombardment. The same way our own moon is covered in impact scars that go back almost to the formation of the solar system. Europa had almost no craters. That single observation stopped planetary scientists cold because it meant something remarkable. A cratered surface is old. An uncratered surface is young. not young in human terms, young in geological terms, which could still mean millions of years. But young enough that whatever was cratering it in the past had been covered over, erased, smoothed out. Something was resurfacing Europa. Something was continuously refreshing its skin. The most natural explanation was that liquid water was reaching the surface somehow, or at least getting close enough to it that the ice above could flow and refreeze and erase the scars of impact. And if there was liquid water near the surface, there might be liquid water far below the surface, a lot of it. This idea stayed theoretical until 1995, when NASA's Galileo spacecraft arrived in the Jupiter system and began a years-long survey of the planet and its moons. Galileo's magnetometer, the instrument that measures magnetic fields, detected something strange near Europa. Jupiter generates an enormous magnetic field, one of the strongest in the solar system, and as Europa moves through it during its orbit, the interaction creates a detectable signal. What Galileo found was that this signal didn't behave the way it would if Europa were a simple rock wrapped in ice. The pattern suggested that something inside Europa was conducting electricity, and the best conductor of electricity that fits the size and behavior of the signal they were seeing is salt water. Not fresh water, salt water, dissolved minerals. An ocean that had been in contact with rock long enough to leach minerals and salts out of it. An ocean that was not a thin puddle, not a buried pond, but a global body of liquid water, wrapping all the way around the interior of the moon, deeper than any ocean on Earth, sealed under a crust of ice that might be 10 to 30 kilometers thick. Europa, the boring cracked billiard ball, was carrying more liquid water than every ocean and lake and river on the surface of Earth combined. That discovery landed like a slow bomb. It detonated not in a single headline, but in the gradual accumulating pressure of scientists realizing what it implied. Where there's liquid water, there might be, not necessarily is, but might be, the conditions necessary for life. Not plants and animals and complex biology, but microbial life, the kind of life that doesn't need sunlight, that eats chemical energy, that doesn't know what a sky is. Life like the organisms we have found at the bottom of Earth's own oceans, near hydrothermal vents on the seafloor, in complete darkness and tremendous pressure, metabolizing minerals and surviving quite happily in conditions that would kill every surface organism on the planet in minutes. For 20 years after the Galileo discoveries, Europa occupied a unique position in astrobiology. Everyone agreed it was one of the most promising candidates in the solar system for potentially harboring life. Everyone agreed it deserved much more attention. And almost no one could figure out how to actually study it because the thing you most want to know about, the ocean, is buried under 10 to 30 kilometers of ice, and we had never built anything capable of reaching it. You can observe Europa's surface from orbit and from Earth. You can measure its magnetic field. You can model its interior based on what you know about its density and tidal behavior. But the ocean is hidden, and the surface, bombarded by Jupiter's radiation, is a harsh and complicated chemical environment that is difficult to interpret from a distance. So we waited. We wrote proposals for landers. We drafted concepts for ice-penetrating probes. We built computer models of what the ocean floor might look like if tidal heating was driving hydrothermal activity. And we looked carefully and repeatedly at that cracked white surface, trying to learn as much as we could from something we couldn't yet touch. Then James Webb launched. The James Webb Space Telescope has been in operations since mid-2022, sitting at a gravitational sweet spot about 1.5 million kilometers from Earth called L2, where it can look outward in any direction without Earth getting in the way. Its primary mirror is 6.5 meters across, built from 18 gold-coated beryllium segments that unfold in space with a precision measured in nanometers. Its instruments are cooled to temperatures near absolute zero so that their own thermal radiation doesn't drown out the faint signals it's trying to detect. Webb was primarily designed to study the early universe. Galaxies from the first few 100 million years after the Big Bang redshifted so far into the infrared that no previous telescope could see them properly. But the same capability that lets Webb detect ancient light from 13 billion light-years away also lets it detect the chemical composition of surfaces in our own solar system with extraordinary precision. In 2023, two independent research teams pointed Webb's near-infrared spectrograph, an instrument called NIRSpec, at Europa. NIRSpec works by breaking incoming light into its component wavelengths and measuring how much of each wavelength is present. Different molecules absorb and reflect different wavelengths of infrared light in characteristic patterns like fingerprints. If you know what fingerprints to look for, you can identify the molecules present on a surface from hundreds of millions of kilometers away. Both teams were looking for carbon dioxide. Carbon dioxide on its own is not a life-detecting molecule. Carbon dioxide is everywhere in the solar system. But the reason they were looking for it on Europa is subtle, and the subtlety is what makes the result so significant. Carbon dioxide on Europa's surface could get there in one of two ways. It could arrive from outside, delivered by meteorite impacts, or produced by radiation acting on organic compounds already present on the surface. If that were the case, you'd expect it to be spread more or less evenly across the surface, or concentrated in impact sites, or distributed in patterns that match the radiation environment. Alternatively, it could come from inside, from the ocean, from geological activity that brings ocean material upward through the ice and deposits it on the surface. If that were the case, you'd expect it to be concentrated in areas where the geological models predict upwelling is occurring. The chaotic, broken, geologically young terrain where the ice has been disrupted from below. Both teams found carbon dioxide concentrated in a region called Terra Regio. Terra Regio is a large stretch of disrupted terrain on Europa's trailing hemisphere, the side of the moon that faces away from the direction of its orbital motion. It's geologically young. The surface there shows signs of having been broken apart and reassembled relatively recently in Europa's history, probably by material or heat from below destabilizing the ice. It's exactly the kind of region where you'd expect ocean material to be closest to the surface. The carbon dioxide wasn't sprinkled randomly. It wasn't sitting at impact craters. It wasn't following the radiation gradient. It was sitting right on top of Terra Regio in the exact pattern you'd predict if it had been carried upward by the same geological process that created the disrupted terrain. The distribution pointed down, into the ice, toward the ocean. Geronimo Villanueva, one of the lead researchers on these studies, described it plainly. The pattern was consistent with the carbon dioxide having an internal origin. It came from below. And that means the ocean beneath Europa's ice contains dissolved carbon dioxide. Carbon, the backbone of every organic molecule that life as we know it has ever been built from. When I first read that result, I had to sit with it for a moment, because it sounds like one more data point on a list. Carbon dioxide detected on Europa's surface. Noted. What's next? But it's not just a data point. It's a confirmation of a chain of reasoning that scientists have been building for 25 years, and this particular link in that chain had never been confirmed before. We knew there was water. We knew there was energy. Now we had chemical evidence that the ocean contains one of the core ingredients of life-building chemistry, and that this ingredient is in contact with the surface in a way that future missions could potentially sample. That's a footnote. That's a breakthrough. But Webb wasn't done. In early 2024, a different team used Webb to search for plumes. Plume activity, jets of water vapor erupting through cracks in the ice and spraying into space, had been one of the most tantalizing and frustrating subjects in Europa science for over a decade. The Hubble Space Telescope had reported possible plume detections in 2012 and 2016. Both detections were right at the edge of Hubble's sensitivity. Some scientists accepted them cautiously. Others argued they were noise. The ambiguity was never resolved because Hubble simply wasn't precise enough to give a definitive answer. Webb is more precise. Webb searched, and the result was not a confirmation of large, continuous plumes, the kind of persistent, obvious geysers that Enceladus fires from its south pole. Those weren't there, at least not during Webb's observation window. I want to be careful here because what sounds like a negative result is actually informative. The absence of large, persistent plumes tells us something meaningful about how Europa works. Enceladus is fed by a relatively stable tidal heating mechanism that keeps its geysers going essentially continuously. Europa appears to be different. The tidal forces acting on Europa are real and significant, but they vary as the Moon moves through its slightly elliptical orbit around Jupiter. The closer Europa gets to Jupiter, the harder Jupiter squeezes it. When it moves farther out, the squeeze relaxes. That cycling of compression and relaxation might produce plume activity that is intermittent rather than constant. Eruptions that happen during specific phases of the orbit when the stresses on the ice shell are highest, then shut off as the stress is relieved. So the picture that emerges from Webb's plume search is not no plumes. It's plumes that are sporadic, possibly timed to orbital dynamics, and not detectable in a random observation window without knowing exactly when to look. That's a more complicated picture than Enceladus gives us, but it's also a more honest one. And understanding the timing and triggering mechanism for Europa's possible plume activity is now a high-priority science goal for the next generation of missions. While we're talking about what keeps Europa's ocean liquid, we should spend some time on the energy source, because it's one of the most remarkable physical processes in the solar system, and it's easy to take for granted once you've heard it explained. Europa is 780 million kilometers from the Sun. The Sun's light and heat, already faint enough at Earth's distance, has continued spreading outward for another 500 million kilometers before it reaches Jupiter's neighborhood. Europa's surface temperature sits at around minus 160 degrees Celsius. There is essentially no solar heating worth accounting for in any model of Europa's interior. The Sun, at this distance, is just a bright star. So where does the heat come from? Jupiter, not solar radiation reflected from Jupiter, not Jupiter's own light, Jupiter's gravity. Europa's orbit around Jupiter is not a perfect circle. It's slightly elliptical, an eccentricity maintained by the gravitational resonance between Europa and two other large Jovian moons, Io and Ganymede. Because these three moons are locked in a 1:4 orbital ratio. For every orbit Ganymede completes, Europa completes 2 and Io completes 4. Their gravitational pulls tug at each other in a regular repeating pattern that prevents their orbits from circularizing. They stay slightly elliptical permanently. This matters enormously for Europa. As it moves closer to Jupiter in its elliptical orbit, Jupiter's gravity pulls more strongly on the near side of the Moon than on the far side, creating a tidal bulge. As Europa moves farther from Jupiter, that bulge relaxes. Closer, farther, bulge, relax over and over again, once every 3.5 Earth days. That constant flexing converts gravitational potential energy into heat. Think about what happens when you repeatedly bend a metal spoon back and forth at the same point. The metal heats up. You're not adding heat from outside. You're converting the mechanical energy of bending into thermal energy. Europa does the same thing, but at an enormous scale. The entire moon is being flexed by Jupiter's gravity, and the heat produced by that flexing is enough. Just enough. Barely enough, but enough to keep a global ocean liquid for billions of years beneath kilometers of ice. Compare that to Io, where the same tidal heating mechanism is far more powerful. Because Io is much closer to Jupiter and gets squeezed much harder, Io's interior is so hot that it erupts continuously from hundreds of volcanoes, making it the most geologically active body in the solar system. Europa gets a milder version of the same treatment, which is why it has a liquid ocean rather than a magma sea. The same gravitational engine that makes Io a volcanic hellscape gives Europa an ocean. The distance from Jupiter, close enough to be heated, but not so close as to be destroyed, is a Goldilocks condition that may have persisted for the entire age of the solar system. And at the bottom of that ocean, the current best models predict a rocky seafloor, not a layer of high-pressure ice like you'd find deeper inside Ganymede, actual silicate rock in direct contact with liquid water. That matters because rock is where the mineral chemistry starts. Hot water circulating through fractured rock on a hydrothermally active seafloor leaches out sulfur compounds, iron, magnesium, calcium, a whole toolkit of chemical energy that microorganisms on Earth's own seafloor have been exploiting for billions of years. If Europa's seafloor is hydrothermally active, and current tidal heating models suggest that at least some regions of it should be, then the conditions at the bottom of Europa's ocean may resemble, in some fundamental chemical ways, the conditions at the bottom of Earth's oceans near mid-ocean ridge hydrothermal vents. Those environments on Earth are now understood to be among the most biologically productive places on the planet per unit area. They support entire ecosystems that have never seen sunlight, running entirely on chemical energy, living in darkness and pressure and heat, completely indifferent to whether the sun exists. We didn't know any of this in 1977, when scientists lowered a submersible called Alvin to the seafloor near the Galapagos Spreading Center and found thriving communities of tube worms, crabs, shrimp, and bacteria clustered around vents gushing superheated, mineral-rich water. The discovery overturned a foundational assumption of biology, that all life on Earth ultimately traces back to sunlight, and opened up a new category of habitable environment that nobody had thought to look for. Europa's ocean, if it has hydrothermal activity, might be a planet-sized version of those vent systems. With more volume, with more time, with more dissolved minerals cycling through it. What Webb added to this picture in 2023 was the confirmation that some of the ocean's chemistry is making its way to the surface. And it didn't just find carbon dioxide in isolation. When the research teams looked more carefully at the spectral data from Tar Regio, they found that the carbon dioxide was sitting alongside other compounds, specifically salts, sodium chloride, common table salt, and magnesium sulfate, which is the chemical name for Epsom salt. Both of these compounds are consistent with what you'd expect to find in an ocean that has been in contact with silicate rock for billions of years. They're the kinds of minerals that dissolve out of rock when hot, acidic water circulates through it. They're, in a very general sense, similar to the minerals dissolved in Earth's own oceans. Their presence in the same regions as the carbon dioxide is telling. It's not just one compound making it to the surface. It's a suite of compounds co-located in a geologically active region, in amounts and ratios that are consistent with having come from the same source, the ocean below. Each piece of evidence strengthens the others. The carbon dioxide is there, The salts are there. They're concentrated together in young, disrupted terrain. The geological models predict exactly this kind of upwelling in exactly this kind of terrain. The picture has a coherence to it now that it didn't have before Webb looked. But Webb also found something that deserves attention precisely because it didn't resolve possible hints of organic molecules, complex carbon-based compounds, the kind of molecules that on Earth serve as the building blocks for biological chemistry. The spectral signatures Webb detected in this category overlapped with other possible compounds, making a definitive identification impossible at this distance with these instruments. The researchers were careful not to overstate it. Possible hints of organics is not the same as detecting organics. The result is inconclusive, but inconclusiveness is not the same as absence. It's a signal asking for a better instrument. It's Europa lowering its voice just below the threshold of what we can currently hear, and it's an invitation to build better hearing. That invitation is being answered by NASA's Europa Clipper mission, which launched in October 2024 and is currently making its long voyage toward the Jupiter system. Clipper carries 9 scientific instruments, the most sophisticated package ever sent to the outer solar system, and it's designed to do everything Webb couldn't. Get close, taste the surface, measure the ice from the inside, and search for signs of biological chemistry in the materials that reach Europa's surface from below. Clipper won't orbit Europa permanently. The reason is Jupiter's radiation. The planet's enormous magnetic field traps high-energy particles that rain down on Europa continuously, delivering roughly 540 rem per day to anything on or near the surface. For comparison, a fatal radiation dose for a human being is considered to be around 400 to 500 rem received over a short period. Europa's surface is bathed every single day in doses that would kill a person. Electronics are more robust than biology, but even the best hardened instruments break down under sustained radiation bombardment. If Clipper parked itself in orbit around Europa and stayed there, its instruments would be destroyed within weeks. So instead, Clipper will execute approximately 50 close flybys of Europa over the course of several years, approaching to within as little as 25 kilometers of the surface during each pass, then retreating to safer distances around Jupiter between encounters. In those brief, close passes, its instruments will collect as much data as they can before the radiation window closes. The centerpiece of the science from an astrobiology standpoint is SUDA, the surface dust analyzer. Its job is to catch and analyze tiny grains of material ejected from Europa's surface by micrometeorite impacts and any plume activity that might be occurring. Every grain it catches is a microscopic frozen sample of Europa's surface chemistry. SUDA can determine the molecular composition of individual grains smaller than a grain of sand. It doesn't need a massive, dramatic eruption to do useful work. Even the faint haze of particles that gets kicked into space by routine low-energy impacts is enough for SUDA to start reading. One grain, one correctly positioned grain that happens to carry a fragment of organic chemistry from the ocean below. That's all it would take to completely change the conversation about whether Europa has the building blocks of life in its ocean. Not proof of life, but one more confirmed ingredient in the recipe. Clipper's ice-penetrating radar, called REASON, will search for liquid water pockets trapped within the ice shell itself. Theoretical models have predicted for years that pockets of briny water might exist at various depths within the ice, sandwiched between the frozen surface and the deep ocean, not connected to the ocean, but formed by localized melting within the ice. If reason detects bright radar reflections at shallow depths, that would confirm the existence of these subsurface lakes. And subsurface lakes within the ice, closer to the surface than the deep ocean, might be far more accessible targets for future landers and drilling probes than the ocean itself. Meanwhile, Clipper's magnetometer will make far more precise measurements of Europa's induced magnetic field than the Galileo spacecraft could manage, allowing scientists to map variations in the ocean's depth and salinity at different locations around the moon. If the ocean is deeper near the equator and shallower near the poles, or if certain regions have more dissolved minerals than others, the magnetic field carries that information, and Clipper will be sensitive enough to read it. Clipper won't arrive at Jupiter until April 2030. That's still years away. But the mission is already underway in a meaningful sense because Webb has dramatically sharpened its target list. Terra Regio, where Webb detected concentrated carbon dioxide and salts in geologically young terrain, is now among the highest priority targets for close flyby observation. The disrupted terrain, the chemical fingerprint, the geological evidence of upwelling. Everything Webb found points to this region as the place where the ocean is most actively communicating with the surface. Webb drew the X. Clipper is going to land on it. Alongside Clipper, the European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023 and is also making its way toward the outer solar system. JUICE is primarily focused on Ganymede, where ESA plans to eventually achieve orbit, but it will conduct 2 close flybys of Europa with instruments that are in some ways complementary to Clipper's. Having 2 independent spacecraft making measurements of the same moon with different instrument suites is enormously valuable in planetary science because ambiguous results can be cross-checked, confirmed or ruled out. The uncertainty that plagued the Hubble plume detections for a decade, was it a real detection or an instrument artifact, becomes much harder to sustain when 2 different telescopes from 2 different agencies with 2 different instrument packages are seeing the same thing. If Clipper detects organics in pseudograins and JUICE confirms anomalous chemical signatures in Europa's atmosphere during its flybys, the scientific community's confidence in those results will be essentially ironclad. There's one more piece of the Europa picture that I want to bring in, because it's one of the stranger and more poetic aspects of this moon's existence, and it connects directly to the question of whether life could survive there. Jupiter's radiation belt, which I mentioned in the context of Clipper's design constraints, does something unusual to Europa's surface. The charged particles that rain down on the ice don't just damage electronics. They interact chemically with the water ice and other compounds on the surface, splitting molecules apart and forcing them to recombine in new configurations. One of the products of this radiation chemistry is hydrogen peroxide. Another is molecular oxygen, O2. Here's where it gets strange. Some models suggest that this radiation-produced oxygen, formed on Europa's surface from the splitting of water ice, gets gradually cycled downward through the ice over geological time, eventually reaching the ocean. If that's happening, then Jupiter's radiation belt, the same environment that would kill a human in hours, the same environment that forces Clipper to execute quick flybys rather than settling into orbit, might be delivering oxidants to Europa's ocean. On Earth, oxygen is what almost all complex life uses to metabolize food. The presence of oxygen in Earth's atmosphere and oceans is both a consequence of life. Photosynthetic organisms produced it as a byproduct and a prerequisite for the energy-intensive metabolisms that make complex life possible. Europa doesn't have photosynthesis. It's sealed under kilometers of ice with no sunlight reaching its ocean. But if radiation chemistry is producing oxygen on the surface and cycling it downward into the water, then the ocean might have access to an oxidant supply that could drive chemistry similar in energy output to the aerobic metabolism that powers most of Earth's complex life. The radiation that destroys the surface might be feeding the ocean. I genuinely find this one of the most astonishing conceptual loops in all of planetary science. It's a feedback system that runs on the very thing that makes Europa's surface uninhabitable, turning lethal radiation into a potential ingredient for biology. It's not confirmed. It depends on how efficiently the ice cycles material between surface and ocean, which is still actively debated, but it's physically plausible, and several research groups are working on tightening the model. Europa doesn't operate by intuitive rules. It is not a place where the obvious relationships hold. It is a place where the mechanism that could kill you is also the mechanism that might be sustaining life. In late 2024, Webb returned to Europa for additional observations, and the results added another layer. The new data revealed patches of what appeared to be crystalline water ice on the surface, ice that was unusually fresh compared to what radiation chemistry should have produced, given the moon's age and exposure history. Fresh ice on an irradiated surface means recent resurfacing. Material from below, coming up, replacing the damaged surface layer with new material. And crucially, the distribution of this fresh ice correlated strongly with the same disrupted terrain in Terra Regio, where the carbon dioxide had been found. This is not a coincidence. The geological activity that creates the disrupted terrain, the upwelling of warm ice or liquid water that destabilizes the surface, the chemical fingerprint of the ocean making it upward. All of it is concentrated in the same place. Terra Regio is not a region where interesting things happened in the ancient past. It's a region where interesting things are happening right now, on timescales that Webb can detect as freshness in the ice. The chemistry Webb found is not a fossil record of a more active era billions of years ago. It's a live reading of an ongoing process. I want to be careful, as I reach the end of this, not to build toward a conclusion the evidence doesn't support. Finding carbon dioxide, salts, and hints of organic chemistry on Europa's surface is not finding life. Confirming that Europa has a global saltwater ocean in contact with a rocky seafloor that may be hydrothermally active is not finding life. Building a model in which all the known ingredients for Earth-like biology are present and have been present for billions of years is not finding life. Life is not an inevitable consequence of habitable conditions. We know that from Earth, or rather, we know it only loosely from Earth, because we have exactly one example of a habitable planet and one example of a planet that produced life, and they happen to be the same planet, which makes it impossible to know whether habitability commonly produces life or whether Earth was extraordinarily lucky. We cannot do statistics with a sample size of one. What we can say is that every confirmed ingredient reduces the number of reasons to think life isn't there. And after Webb's observations, the list of confirmed ingredients on Europa is longer than it has ever been. There's also the question of time. Life on Earth appears to have originated remarkably quickly after conditions became suitable for it, within a few 100 million years of the planet forming, possibly faster. Europa's ocean has existed, by current estimates, for billions of years. If the origin of life is a chemical process that happens given sufficient time, raw materials, energy, and liquid water, then Europa has had the time, it has the raw materials, it has the energy, it has the water. Whether that's enough, whether there's something else necessary, some additional condition or event or cosmic accident that Earth experienced and Europa might not have, is the question we don't yet have the tools to answer. But we are building those tools. Clipper is already flying. Juice is already flying. The concepts for a future Europa lander are already being developed at NASA. And the science case for it keeps getting stronger. If you could somehow stand on the surface of Europa, if the radiation suit held, if the temperature was manageable, if you had brought enough shielding and you looked up, you would see Jupiter. Not the way you see the moon from Earth. Not as a disk in the sky that you can cover with your thumb. Jupiter would fill nearly 24 degrees of your field of view, about 48 times the apparent diameter of the full moon as seen from Earth. It wouldn't look like a planet in the distance. It would look like a wall. A banded, turbulent, slowly rotating wall of orange and brown and white, its great red spot, a storm that has persisted for hundreds of years, drifting across the face like a slow bruise. And you would feel, in a way that no photograph or simulation can adequately convey, the full weight of what it means to exist in that gravitational field. Every tide in Europa's ocean, every crack in the ice beneath your feet, every molecule of carbon dioxide deposited on the surface of Terra Regio, every potential hydrothermal vent on the ocean floor 4 hours below you, all of it traces back to that wall of gravity pressing down from above. Europa doesn't exist independently. It exists because Jupiter allows it to. It has an ocean because Jupiter squeezes it. Its surface is lethal because Jupiter irradiates it. It might have life because Jupiter provides both the energy and the oxidants necessary to sustain it. The same planet that makes the surface uninhabitable makes the ocean potentially hospitable. At every level, the story of Europa is the story of something extraordinary being forged inside something overwhelming. That tension is what makes it compelling in a way that goes beyond science. It's a story about conditions that should preclude life being exactly the conditions that enable it. About a place that looks from the outside like nothing and hides from the inside like everything. Before Webb, Europa was a candidate, a promising one, a scientifically well-supported one, but still a candidate. A place we suspected might have the right conditions, argued might have the right chemistry, hoped might have the right history. After Webb's observations, Europa is something closer to a case. A place with confirmed liquid water, confirmed internal carbon chemistry, confirmed salt composition consistent with prolonged rock-water interaction, confirmed geological activity reaching the surface in real time, and a sharpened target location where all of that activity is most accessible to future instruments. The case is not closed, not by a long distance, but it is no longer primarily theoretical. There's a difference between a hypothesis and a research program. A hypothesis is something you think might be true. A research program is something you're actively testing, with specific experiments and specific measurements and specific predictions that could be confirmed or refuted. Webb has moved Europa from the first category to the second. Clipper will make those tests. Suda will catch the grains. Reason will map the ice. The magnetometer will read the ocean's depth. And if everything goes according to plan, we will know more about what's in Europa's ocean in 2031 than we have learned in the entire previous history of science. And one day, in the 2040s, maybe later, depending on budgets and political will and a dozen other factors that have nothing to do with the science, a lander will sit down on Terra Regio or somewhere nearby, and a drill will push through the ice, and an instrument will be lowered into water that has never seen sunlight, into an ocean that has been sealed for billions of years, into whatever is down there. If that instrument finds barren saltwater with interesting minerals but no biology, that will be an important and clarifying result. It will tell us something about the probability of life arising under those conditions. and it will redirect our attention elsewhere. If it finds something that looks like the building blocks of biology, amino acids, lipids, nucleotides, but no living cells, that will be one of the most important discoveries in the history of chemistry, because it will tell us that the universe generates the ingredients of life wherever conditions allow, and that those ingredients are not unique to Earth. And if it finds something that metabolizes, reproduces, and evolves, if it finds life, it will be the most consequential discovery our species has ever made. Not because it solves everything, but because it reframes everything. Because it means that life is not an accident that happened to a particular planet in a particular corner of a particular galaxy. It means that life is something the universe does, repeatedly, wherever the conditions allow, and that the conditions appear to be far less restrictive than we ever thought. Europa has been quiet for 400 years. It was quiet while Galileo pointed his telescope at it, and it was quiet while Voyager photographed its cracked surface, and it was quiet while Galileo's magnetometer read the salt in its ocean, and it was quiet while Hubble squinted at its atmosphere looking for plumes. And then James Webb looked, carefully and precisely and patiently, with the best instruments humanity has ever built, and Europa finally had something to say. We're still translating, but we're listening now.